Hi guys. So I took class at 3 p.m. to 4 p.m. But uh, my screen froze at after some time, and the recording couldn't happen. So I continued the class, but I'm doing this again for the recording. And the class went very well, in which I solved two questions, and there was we solved one question, but here I will solve two questions, and there were some questions asked before the class, and some of them I am mentioning them again. So our first question was, there are a lot of alphabets and symbols in the course. So outline? Is there any outline to the structure of the course? And I am getting a little bit confused. So, so his doubt was generally like why we are doing this, and what is the general format of applying finite element method and some sort. So, uh, so I just told him that the aim is to find the solution of a physical model, and before that, we have to do something called abstraction, which is nothing but uh, converting the physical model into a mathematical model. This mathematical model have some assumptions into it. So it's kind of any reality is converted into first mathematical form, and then we try to capture the physics of the problem, or we wanted to find some relevant quantities in the problem. So we try to approximate everything, because the problem is we cannot find the exact solution of each and every problem. So hence we kind of we come to this finite element method, and here is the rule of finite element method. So this model has a approximate solution. So this has a approximate solution, and that is find out using finite element method. For example, let's say we have some eraser, because actually everyone had uh, this example. They have observed the example when we can do the bending, and we can also do little bit axial, uh, but whatever we have studied in this course, um, it is just idealized form of it. For example, if we take as a bending, so in that to pure bending, so it is something like this. So Euler-Bernoulli beam principle tells that this cross section remain parallel to each other, or normal to the plane of bending. So hence this is always perpendicular, but this is not real solution, because actually it is something like this, and which is covered in Timoshenko beam. So let me just, so this is Euler-Bernoulli, and this is Timoshenko. So, which is more real? Timoshenko is more real. Albert Bernoulli is more ideal form. So, our main aim is to convert the physical model into some problem in this course, that is SKU is equal to F, where U are generally shown by displacement, a displacement vector, and force is generally this is a force vector, and this is our stiffness matrix. Okay, so this is a symbol which we have used throughout the course, and in Jane Reddy book this is there. So the stiffness K is a matrix, and it depends on how much nodes we have taken, as well as um, mm, yeah. So here the discretization come into the picture, how we are describing the system. So we are converting the large body into some smaller pieces, and now um, we are formulating for this smaller piece, that is called a weak form of one element, and then we are providing so we are assembling it, and then finally we get a global matrix, and we try to solve it and find the value of missing U and F. So this is the general procedure by which we start with a physical model, and then uh, so we start with, in this course we start with a mathematical model actually, and so abstraction is not covered in this course. So that physical mathematical model we try to find the approximate solution out of it, and finally we get a finite we use finite element method to find approximate solution. Okay, so this was the first question. Then second question was, is there any method by which we can get natural boundary conditions of the system? So yes, there is one more method by which there are actually many methods, but one method which you have studied from the 9th, 10th, 11th, 12th class is called Newton's law. Newton law is nothing but drawing of FBDs, free body diagram, where we take a part of the free body, and then we try to uh, put the force direction. For example, if this block of mass m is moving in this direction as x, then it will have some D'Alembert force as this. So this we can find out using Newton law also. So this is just like a natural boundary condition or force condition. But why we are not using in academic or in scientific way? Because Newtonian law has lot of problems, because for each particle we have to look at the direction of the forces, and we have to equate them. So it takes a hell lot of time if it's not generalized. So hence for generalization we use something called Hamilton law or language equation of motion. So what that do, that it generalize the system such that finally we get a governing equation as well as boundary condition, natural boundary conditions. And what does this method require? This method require only the energies in the system, and also essential boundary conditions. So if we have these two things, so we can apply Hamilton law and language equation of motion or language equation of motion, and we can get governing equation, natural boundary condition. Now in our case, where we are using Hamilton law in, let's say, 1 degree of freedom, which is given in the above figure, we can write its governing equation as mx dot is nothing but a there will be some force which will be like this, so plus uh, uh, is equal to 0. Okay, so force plus mx x double dot is equal to 0. So this is our governing equation. In natural boundary condition, we can see this as there will be normal and here will be mg. So this is also a governing equation, but this can also be natural boundary condition. But for large particle or for continuum, the Newton law loses its power because we have to be keen in the directions. There are generalized method for Newton laws, but uh, Hamilton law, the requirement is simple. We need a scalar energy, and we can find out how the configuration is. So the final result is getting out the governing equation, natural boundary condition. Now, Hamilton law and Lagrange equation of motion have its root called calculus of variation. So it's so wherever your term use first variation is equal to 0. Is it nothing just like finding the maxima and minima of a uh, so in when we were finding the maxima and minima in our 8th or 10th class, we saw that we used to find the derivative of the quantity, and we were putting the derivative is equal to 0. Then we were finding the double derivative, and we were to finding if it's greater than 0 or less than 0, which will give us that it is maxima or minima. Similar approach is calculus of variation, where instead of a function, a functional is there, and we find out the first variation of it if we put it as 0, and that gives us our Hamilton law, and we can convert the Hamilton law into language equation of motion, because that we can do in by using Euler language formulation. So So let me answer the related question. Fourth question: what is delta operator? So delta operator is called variation. To explain visually, so let's say this is a 3D diagram, and this is y, this is x, and this is z, and there is some surface. Let us take this as y. Let us take this as y, and this is z, such that z is a function of x and y. Okay, let me show it more visually good. Okay, so my mouse is not working properly, but I will first. Okay, so let's say this is a surface on a 3D surface, and the z is a function of x and y. Now, if somebody say what is dz, so dz will be some small area dx and dz, or dx and dy. If we take that, so dz can be defined as that. Okay, so what is mean by this? This dark green thing. Okay, but what del z means? Del z means this, like having a different surface altogether, such that having this together such that the ends are same, but it is having a different surface. Okay, so ends are same, but it is kind of, let's say, having this surface. So having a different topology is what I mean. So having a different topology. Okay, so this thing is called del of z. So d of z is this, and del of z is this. So it's a variation of a functional as compared to a small z. It is variation of z. In English language, it means nearly same, but mathematically, it has a huge difference. Now, how does ANSYS and Abacus software work? So, the general format is they convert the mathematical model into matrices, and they solve that matrices and find out the solution, and then pre-process the data and gives us other solution, like whatever is required from the model. So the first step is discretization, and so that is called meshing. So let me write down. So we provide mathematical model, then we mesh it. Mesh is nothing but uh, discretization. Then we provide governing equation. Now this governing equation can vary. So how much accurate we are taking depends on how complex it is. So for example, we have learned Euler-Bernoulli as well as Timoshenko, and we saw that governing equation for Euler-Bernoulli and Timoshenko are different. Timoshenko being more nastier one, and Euler-Bernoulli is much simpler than Timoshenko. But so it's like idealization. So this is more over the more ideal, and this is more real. Okay, so the graph goes like this. They are much more geometrically um, correct beam model, which you will eventually study if you are into the research. So, and we provide governing equation, and we define for one element, and then we try to find k matrix, and then from k we solve the system, and we find u and f. Okay, and then we pre-process the data to find all the thing which is required. We will solve one example today related to that. Now, what is equivalent stiffness? So to answer this, first of all, the body should be flexible to have a stiffness, the value of K. Actually, what does K equivalent mean? That is the question. So in the eraser, so instead of a spring, if you put a eraser there, such that it is compressed like this. So if we have a spring and we compress, sorry, I have a spring actually. So if we have a spring and we give some force like this, okay, some compressive force, some force like this. So what will be K equivalent? So K equivalent will be nothing but EA by L, and this we saw in our one of the example. Similarly, torsion has GJ by L, so similar kind of quantities, and bending also have similar kind of quantity. So my point being that so K equivalent can be found by using what type of physics you wanted to capture. So if you are taking the same eraser and now we are saying that we are bending it such that it we are giving it this kind of a force, okay, so that it should get perfect circular shape. And now we wanted to find stiffness. So we wanted to find the equivalent stiffness. So as you can see, this won't be equal to EA by L. It will be equal to something else, which will be bending stiffness, not the axial stiffness. Okay. Similarly, go for torsion stiffness. So hence, equivalent stiffness means like which physics we are capturing, and it varies from various situations. Now we will solve a question. So these were the question which I kind of repeated. It was asked in the class, and okay, I will start the question now. Uh, just a second. Okay, so we already know that K equivalent axial K equivalent of an element. Now first we will define what an element is. So element is this. Okay, and so what its value is EA by HE, HE being the length of the element, So this is our K equivalent. Here finding stiffness for element 1. So EA by HE, which comes out to be, so the values are given. E is 72 GPa, Similarly, stiffness for element 2 we can find out. This is for 1. So which is same as stiffness 1. You'll find stiffness for element 3. So which gives us all the stiffness for the all the element. Now we have to assemble the stiffness into global stiffness. So these are the local stiffness. Let me write local stiffness for element 1, local stiffness for element 2, and local stiffness for element 3. Now we'll find global stiffness. So we're taking it common. 1 minus 1 minus 1 1. Now 1 plus 1 minus 1 minus 1 1. 1 plus 1 minus 1 minus 1 1. And others are 0 0 0 0 0 0. So this is our K matrix. Now we will define our U matrix, U vector and F vector. So this is 2, this is also 2. So let me write f, which is nothing, f1, f2, f3 and f4. So these are those points 1, 2, 3 and 4. We know the forces at 2 points and 2 points we don't know. So f1 we don't know. f2 is given, which is p1, and f3 is p2 but in different direction, and f4 we don't know. Okay, so this is our force vector. We will just transfer it here. Also there will be u vector, which is u1, u2, u3 and u4. Now here we know that u1 and u4 are 0 because it's fixed. So 0, u2, u3, 0. So we will transfer this also here. Let's put the values also. So P1 is given as 100 kilonewton and this is minus 200 kilonewton. So let's put everything into SI unit F4. So next what I will do is so we have Ku is equal to F, and from this we will find, so these are four this is four equation and four variables. Okay, four equation, four variable problem, linear problem, and hence it is solvable. Uh, let's solve it. First value of k into u is equal to f. So let us write all the equations. So it might take some time. 72 into 10 to the power 6 into 0. This into 0, this into u2. So minus 72 into 10 raised to power 6 into u2, then again 0 0 is equal to f1. Next equation is this into 0, then 2 u2, 2 means 2 into 72 into 10 raised to power 6 u2 minus 72 into 10 raised to power 6 u3 is equal to 100 into 10 raised to power 3. So from first we found out that minus 72 is this, so actually this is this, and hence we can put 2 into f1 minus 72 into 10 raised to power 6 u3 is equal to 100 into the power 3, which gives us 72 into 10 raised to power 6 u3 equal to 100 into 10 raised to power 3 plus 2 into f1, which gives us value of this. or actually we can again do things because that will be required now. So third equation we can write as 0 0. Um, so this is first equation. This was second equation, and we have used first equation in it. Now third equation, minus 72 into 10 raised to power 6 u2 plus 2 into 72 into 10 raised to power 6 u3 is equal to minus 200 into 10 raised to power 3. So we can put value of u3 or 72 into u3. So actually minus 2 into 100 into 10 raised to power 3 plus 2 f1 is equal to minus 203. And fourth equation is u is regarding u3 and f4. So we can convert value of u2 into f1. So before going to the fourth equation, we can actually put the above value also, so which comes out to be minus f1, so minus minus plus f1 minus 200 into 10 raised to power 3 plus 4 f1, so minus 4 is equal to minus 200 into 10 raised to power 3. That goes there. This is minus 3 f1. I think I made mistake somewhere. Minus and this 72 to come here plus only become minus minus minus. So actually it's coming as 0. Kindly check. So f1 is 0. Wrong. Minus 22. And problem started here. First is okay. So this is minus 72 equal to this 0, and then this to u2 equal to okay, and from that we found out value of u3. Hmm. Okay. And third equation is this into this and this into this. This is 0, 22 terms. Minus 22 and that is plus. But this number to be negative, negative. Something is wrong somewhere. Okay, let's not convert it as of now. And third equation, fourth equation, let's write fourth equation is u3. So minus 72 into 10 raised to power 6 into u3 is equal to f4. In first equation u2 and f1 is there. In second equation u2 and u3 is there. And second and third equation has u2 and u3. So let's try to solve these two. Let's not convert anything into any one. We have to find u2 and u3 and our problem is solved. So 2 u2 minus u3 is equal to 100 into 10 raised to power 3 by 72 into 10 raised to power 6. And here what happens is minus u2 plus 2u3 is equal to minus 200 into 10 raised to power 3 by 72 into 10 raised to power 6. Now we can multiply it into 2. This will become 4 and this will become 4. Now adding second equation and third equation we get 3u3, right, is equal to 100 into 10 raised to power 3 to 10 raised to power 6 to 10 raised to power 3 by, which comes out to be So U3 came at to as like this, and U2. No, vector is coming 0. So F2 is 0. Oh, F1 is 0. There is no reaction force in one wall, and F4 is minus 72. Hmm, 100 kilometer. Now next step is to calculate the stress in element 1 having node 1 and 2. So not element E having node 1. So we know that sigma is equal to F of A. So it sigma so sigma of a element will be equal to 1 by A of the element F of element, and this is equal to EA by HE A 1 minus 1 minus 1 1 U of E U 2 of E. Yes, like this. A of element. So this is the formula for sigma. So for example, stress in this is all about axial stresses. E E and what is A? Oh, is it cancel? So E by H. This into U1 U2. As we have seen that it's 0. So stress in element 1 is 0. Stress is element 2 having node 2 and 3. So I'm just writing out the values here. Therefore, but we have to find actually the total stresses at the nodes. Sigma 1 is straight. Sigma 1, because it one only one is there. Now what about sigma 2? Sigma 2 has two stresses. So one coming from 1 and another coming from 2. So this is first. Sigma 3. And again sigma 4 is only 1, which is because of the element 3. And from this we can find out this is our maximum stress. Now, as you can see, it took me about an hour to solve the whole problem, and this is the most of simpler of the problem. So actually, there were three elements, and we were trying to find the axial deformation and axial stresses into the system, and we found out for one element, and then we try to assembly the whole system, and then we found out the global stiffness, and then we put into the equation, linear equation, and then we solved it. So in very messy way I solved. Actually I was having doubt like why it became zero, but I actually it came as zero. And then we find out the forces as well as displacement, and then stresses. So commercial software also do a similar job. Where it is different is it takes a hell lot number of elements, and this k equivalent is also different. So this is very linear problem. So our k equivalent is very nice, but it is very nastier in sense of which model we are taking. So I hope you learn from this class. This is just a practice problem to which contains a stress strain. I will now stop the recording and I will upload this sheet. Thank you guys.